Okay, so the second problem, 4.36, this is to bend the bar about the vertical axis. And vertical axis here is the y-axis. So the bending applied in this way. For example, the beam will be curved toward the z direction or in the opposite direction, either way. And so now the bending moment about the y-axis, which define the directions where the neutral axis is pointing to. So if we draw the cross section is looking at here, the kind of small piece. So the cross section here, this is z direction, and upward is y direction, which means you look at the beam from this viewpoint. Okay, and that's a cross section. So neutral axis pointing to where the beam is bent over, bent about, the moment is bent about, which is y. So here, this is the neutral axis. This is a very key, very important step. And the next step, we obtain the transformed cross section. And for example, if I choose aluminum as the base material to homogenize the whole cross section, so we first calculate the scaling factor N is obtained by dividing the material to be transformed by the base material, which is EB divided by EA 1.5. And then this is a cross section of the transformed shape. And here is the way we widen the dimension of the material to be transformed, which is brass, in the directions of the neutral axis by 1.5 times. So here is originally is 32, we widen to 48, and evenly on both sides. Material 1, aluminum, is the base material, so we keep the same dimensions here. So based upon this transformed cross section, we calculate the moment of inertia. Let me take the transformed cross section into two portions, portion 1 and portion 2. So the moment of inertia respect to the neutral axis, okay, is the summation of the two. For material 1, and here the two strips, so 2 times of the each strip, and here we apply the parallel axis theorem, obtained the moment of inertia for this beam about this axis passing through the centroid, which is this term, plus the A times distance squared from the neutral axis here is 20, so let's go to this term. Now for the second portion, and that is a little bit more straightforward, just like this. So we obtained the moment of inertia is 355 times 10 to the minus 9. The next step, we calculate the stress, the magnitude of the stress on the transformed cross sections. Let's see, now is a neutral axis, and according to the generic formula, m equal to sigma equal to minus my over I. M is the magnitude, y is the distance measured from the neutral axis to where we are interested. So for this example, we're looking for the maximum value. So the maximum value on portion 1 will be either along this side or along this side, and the distance either side will be the same, measured from where the sides to the neutral axis, which gives 24 millimeters. So the maximum value on the portion 1 is equal to m times yes, so we look for here. So the maximum value is on this side, or on this side is m times y. Y is the distance measured again from this side to the neutral axis, equal to 24 millimeters. In a similar way, in portion 2, which is the two strips here, the maximum value in portion 1 in portion 2, in portion 2 occurs either this strip, this, or here, either side. And here we only focus on the magnitude. So y, again using this formula, y is the distance measured from where we're interested. Here is the maximum to the neutral axis. The distance is 16. So m times 16, and I is previously calculated. Once we calculate the needed information, the stress on the transformed cross-section, we translate it onto the original cross-section. So again, this is our neutral axis. So we're looking for the maximum value on each material for brass that occur here or will occur here. In aluminum, will occur here, 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 or here. And the value being calculated is this. In the aluminum, that is directly the same as the transformed. So we directly put into this formula. And for this design, asking to less than or equal to the allowable stress. So we put in here, we calculate the moment like this. And for the brasses, that is the transformed from here to here. So we have to remember to calculate the scaling factor 1.5. And then we calculate according to this criteria. We calculate the m is less than or equal to this number. So we compare the two values. The final answer should be pick up the smaller one, and here's 1.58 kilonewton meters.